it's always great to continue the journey of how we do testing with Dyno.
Yes.
In our last podcast, we brought some good insights about what all Dyno can be used for. I think today we will discuss more insightfully about one specific topic, that is importance of SOC, state of charge of a vehicle, and its performance with respect to it, and how do we use Dyno to utilize for its test cases, and to draw the overall beautiful graphs that can come out of it. And I think we can also add a bit more topics of, I think, the SOC itself as a component to people who might have not very well immersed on understanding its behavior as a characteristics.
Yes.
So that's a good interesting journey to talk about it today. And we have done a lot of tests on our dynos for a couple of vehicles that we have got the data. I think we will discuss more insightfully about that reports also, and that gives the realistic results of how it is happening. So I think that's the set context of what we're going to talk today, and using Dyno, Chassis Dynamometer, and then study the test case of impact of SOC on vehicle performance, right? I think it's good to start to understand what is SOC at the basic level.
Yes, absolutely.
I think you would be the right person to get deeper idea of how and what SOC is, and then also maybe help us in relating a bit more at a cell level, what's happening, right? So let's start with you about that. Yes.
Sure. So when we talk about electric vehicles, right? So battery is the one that is powering all these vehicles.
Yeah.
So in a fundamental level, the cell is the basic power unit.
Correct.
In any EV. So there are different form factors of cells. Some are cylindrical, some are prismatic, all these things. So essentially, they are all chemical devices which power the electric vehicles.
True.
So they also, during their operation and during their their lifetime or one charge cycle, once you fully charge and then you fully discharge.
Right.
So they won't exactly power throughout.
Okay.
The power won't be continuous or constant throughout.
Right.
So it varies. So when it is fully charged, it can give you a lot of chemical will be built up there, and it will give you a lot of energy at the beginning of the when it is discharged.
Right.
So when it is as the charge decreases, we can expect much less performance out of the cell.
Right.
So to analyze that, I want to open a data sheet.
Sure.
Right. So in that way, we understand better on what exactly is happening.
Sure.
So this is one cell data sheet that we have currently.
Right.
So I want to specifically open one graph here, so which specifies something like different discharge rates.
Okay.
That how much of current that is being currently discharged.
Right.
And with respect to some temperature. So right now we'll consider only for the 25 degrees Celsius temperature. And here are the C ratings. So C rating is nothing but if the cell is, let's say, a 5H cell. So if you're drawing 1 amp or 5 amps of current, so that is equal to 1C.
1C, right.
That means that it will be discharged by 1 hour.
Got it.
So 1C will get discharged over 1 hour.
Right.
So and however 2C discharged over 30 minutes.
Got it. Right.
And C means it is 20 minutes.
Right.
3C means it will be discharged in 20 minutes.
Got it. Right.
So something like this. So this particular test, they have done it for, you can see 0.1C, 0.3C, 0.5C, 1C, 2C and 3C.
Right.
All the different discharge rates.
Right.
So here if we take a look, right, the voltage will be at the,
the highest one.
one.
The SOC is full, that's what you're saying. Right?
Whenever the SOC is full, let's say we consider SOC is 100%. The voltage will be anywhere between 4 to 4.2 volts.
If it is an NMC cell.
Yes, if it is an NMC cell.
Right.
So it depends on the chemistry as well, right? So if it is an LFP cell, it will be 3.65 or 3.4, somewhere in that range. Right. So once it is slowly getting discharged, so in this particular cell, what we can see, it's around 108 cell.
Right.
So whenever it is slowly discharging, so we can see there is a drop in cell voltage.
Right.
So it's anyway, it starts from 4.2 volts to 2, it will drop till 2.8 as well.
Right.
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 And one can observe, the curve is linear at the beginning,
Right.
and at the end we can see it suddenly drops. The voltage, there is a sudden voltage drop in the cell.
Got it.
So the vehicle also behaves in this aspect,
Right.
and depending on how the manufacturer is tuned it,
Right.
and what is the cutoff limits, and how he has set the limits, right? So if we consider the cell as a single unit, this is how it performs.
Got it. Right.
Right. So what we'll do now is we'll take one reference from one of the
Right.
the vehicle test cases that we have done.
Okay.
Right. So that was an Ather vehicle.
Right.
So we'll see how for different SOCs, what is the performance the vehicle is delivering.
So if I can just pick a small idea just to get a relevance, that means to say that the cell is not a constant voltage source.
Yes.
So cell will change its voltage output with respect to the capacity.
Yes.
So we say that the cell is fully charged, maybe it holds about a 94 Ah, I think, relatively around the values. And then when you remove the capacity out of the cell, the voltage start to drop down. So that would be a typical terminal voltage characteristics of a cell.
Exactly.
So what you intended to say is that there is a good region that is very happy to operate, where there is not much of sudden drop of voltages. But at some point, maybe somewhere about like at the end of discharge, maybe it's close about 3.4 volts and 3.2 volts, like somewhere around that range, the cell exhibits a sudden drop in voltage. And that would be because of some inherent internal characteristics of the cell. That's what you mean to cover. And according to that nature, we need to make sure that the operating range of an output of the battery need to be limited, so that you may see better characteristics of vehicle performance. So if you tend to operate slightly below that, then if they have not calibrated very well, then you would see a sudden drop in performances and things like that. So you would help us relate this more by conducting tests on the dyno that we have done on the Ather 450S, I think.
450 yes or plus,
Yes, model that currently we have. So yeah, let's dive into it more deeper, understanding the test cases that we have done.
Yes. So we'll correlate what is happening in the vehicle side and with the cell side. So we'll get much understanding on where the vehicle is standing, how it is performing as well.
Right.
So if we quickly open one of the test data, so this was the maximum performance and maximum speed validation test with respect to SOC. So the vehicle was Ather 450. So I'll just quickly go through. This is all the summary. I'll just quickly go through the graphs.
Do you mean to say that we did this test? Can you give me a context of how was this test done? Okay, you charge the vehicle to 100%.
Yes. Coming to that. So the vehicle was completely fully charged to 100%, let's say, right? And it was stayed idle for some time, let's say for 3-4 hours before the test is started. Test has started, right? Yeah. So then we do a performance and acceleration test at, let's say, 100% SOC, or it might be 99 or 98, close to 100%.
Right.
So then we do the test with respect to different grades and maximum loading as well.
Got it.
Right. Then we discharge continuously. The vehicle till it comes like 95% or 90% SOC. Then we'll let it stay
at that
rest for 1 hour at least. Then we repeat the test again. So like this, the test is repeated for different SOCs. Let's say 100, 90, 80%, 70%,
at 10%
60%.
intervals.
So at the lower SOCs, we've done it for 5% difference.
Intervals in place.
Something like 20%, 15%, 10%, 5%, even 1% as well. So 0%, of course, the vehicle will stop running. So till 1% also we have done
able to test. So if I understand that, like we charge the vehicle to 100% and then we give a rest. So at 100% SOC, we do an acceleration test. Is that, if I'm understanding right? And then you do it at which mode? Because Ather has like, I think 3 or 4 modes of operation.
So we consider the maximum mode. whatever
Okay.
that
That's
is
like
there.
sports mode?
Yes,
Okay.
sport mode.
Okay,
Yes.
okay. So then in that case, maybe at a lower SOC, I don't know, like it's below 25, 30%, the vehicle switches back to automatically to.
Yes, exactly. So what happens below 20%?
Okay.
So as soon as it comes 19%, right?
Right.
So whichever the mode the vehicle is in, it automatically shifts to the eco mode.
Eco mode.
So
Right.
there we can see a drastic vehicle performance drop.
Okay.
So that is one reason where this region, whatever
Got
we
it.
talked
Like when
about,
you're coming nearby to
coming near to this region, so
Right.
they switch to eco mode.
Right.
So that is one way they're doing.
Okay.
And we'll also see how gradually the vehicle performance also
Decreases. So it's not like a drastic jump in performance.
Yes.
So you would see a very, very decently developed algorithm that derates itself in a very neat and decent fashion.
Yes. So that will be in the very lower SOC region. That is somewhere below the 20% region, 20% to 1%.
Okay. Interesting.
So what we currently have here is the motor torque and motor speed
Right.
characteristic for different SOC. You can see here
Right.
it starts from the 100 SOC
Right. And then slowly
till 20%. Then upon the 5% interval, we have 15%, 10%.
Nice.
So all this thing.
Okay.
So we can see till the 20%.
Okay.
Right.
Okay.
We are seeing almost
It's
equal
just-
performance. So
right.
there is slight variation
Right.
depending on the temperature and all this, but we can assure that it is maintaining
Pretty good outcome.
pretty good outcome.
Right.
So whatever it is doing at let's say 80%, it is still doing the same thing at 30% as well.
Right.
So
Right.
that is what specifically this graph is telling.
If I understand this, we are trying to relate torque.
Yes.
Then we can relate that to a power.
Yes.
So, because maybe for the understanding of everybody who's listening, so that we're talking about a battery, but we're talking about a motor over there.
Yes.
So we can correlate. That's what you mean, because you're doing a mechanical measurement and then we can relate it to an electrical measurement. That is obviously in relationship with the output electrical power that we are
Exactly. Exactly.
Okay.
Yes. So here, what we can see here, there are two grouped curves. So one is with the high performance. So this is which was done in the sport mode.
Sports mode. Right.
Right. As soon as the vehicle reaches below 20%,
Right.
so it's switching to the eco mode.
Got it.
And this is significant drop in the performance
Right.
here as well.
Right. Right.
So and one more thing we can observe is the 3% and the 1% curve. Right.
There are.
So when the vehicle reaches, let's say, below 5%,
Right.
something like 3%,
Got it.
so there is even further drop in the performance.
Right. Right.
Right. In the after the setting
Got
speed.
it.
Right. In the 1%, still it is achieving, but
It
we
is
can
able to
see
do its the best as possible.
yes, it is trying to do its best.
Right. Right.
So
That means they've done some really nice engineering behind to make sure it's not like at below 10% SOC you don't get to drive your vehicle or anything like that. Maybe even you can drive like 5-6 kilometers or something like that. Possibly, I think so.
yes.
Right. Even that about a 10% SOC you can achieve that. That's really nice.
So this is where the dyno also comes in actually.
Right.
So where if a user is driving the same vehicle on the road,
Right.
he might not experience this slight performance drop.
Exactly.
He might
But
not
you're able
experience.
to,
Yeah, because even when we are doing the test, we couldn't observe any difference
on the road.
on the road.
Yeah. Yeah.
So when we put it on the dyno,
Yes.
so this
you can really
yes
and precisely say,
precisely
this
say
is
yes.
how it is performing.
Yes.
This is how it is repetitively performing as well. Right.
Yes.
Right. And that way we can tell the motor controller to limit its output current and all of that. So that maybe I think if I connect it back, when the cell voltage is slightly dropping down, maybe the SOC is about 20% or something like that. If you give a sudden throttle because of the higher current, the terminal voltage will drop more drastically. That would hit under voltage cutoff characteristics and things like that.
Yes. So speaking of that, if we go back to the data sheet, right?
Right.
So in this region, in the 1% region, they are operating somewhere around this region.
Oh.
Where it is typically between 3.5 to 3.4 volts.
Right.
So what they are basically trying to do is that at 0%, they are cutting off the vehicle in this section itself.
Wow.
So they are never even letting the vehicle go near the polarization region, or what we call it the sudden drop of the voltage
drop regions.
So they are never even letting their vehicle go that region.
Go till there that point.
Yes.
Right. So do you mean to say that I think the cell's DOD is between voltage as an operation to 4.2 to 2.8, but in realistic world, but they want to make sure that is limiting somewhere about 3.4 itself.
Yes.
And about 3.4, 3.5, so that you don't go in by that way that DOD of the cell has been restricted.
Yes.
so that you get in performance
Yes.
and you don't go to under voltage cutoff conditions and things like that.
Yes.
Interesting, right?
And one more very important thing I want to focus is that in this region, if the cell is hitting this region often, so it will affect the cell health significantly.
Right.
Right. So then they don't want to do that. So it's a very good, so that the range is also not dropped further as it is continuously
operated and things
operated.
Like that.
Yes.
Right.
So and it also helps preserve the battery health.
Got it.
So that is what the
long-term perspectives of retaining the lower DOD operations in place.
Exactly.
Right.
So upon this, we do also have a certain log for the current as well. So, but currently it is not in this document.
Right.
So that will be discussed later.
We can bring that in the upcoming podcast.
Yeah, that will be there. So we'll go further. So we'll see what are other things we have. So once again, I want to mention that we did it for different gradients as well. So one is for 0%, something like a flat road.
Right.
And one is for the 7% as well.
Okay.
But here we can see that there is a significant increase.
Right. The torque. Yes.
So we are demanding more torque from the vehicle, and it is delivering.
You're telling that you're on a gradient right now.
Yes.
And that's another function of the dyno
as well. Yes.
To recreate a gradient conditions as like a real world. So you're going uphill and things like that. Maybe you're coming out of a parking lot.
Yes.
All of that we are able to replicate.
Yes.
So this is at a 7 degree. Right.
So this is the 7 grade, and we also have a 14 grade as well.
Okay.
So we can see with the 7 and the 14 grade, the speed is very limited.
Okay.
So it is pushing hard as much as possible.
Okay.
With the consumption of torque,
right,
there is a slight reduction in the speed.
Got it.
Because the power is limited in that region.
True.
And during the lower SOC specifically, we can see it is reaching maximum of 2000 of motor speed.
It's like motor is trying to draw a more amount of current.
Yes.
And that is kind of limiting the operational. I would say the power as such is slightly needed higher, deliver the output torque, and that way we are not able to go to the higher motor speeds operations, but you're staying a little below, but still able to move the vehicle with the lower performance characteristics in place. Right.
Yes. So by this we can also tell that even in the lower SOC condition.
Okay.
So what can be the vehicle performance?
Right.
Whether there is a ramp there and whether you can go up this ramp or not.
Exactly.
Let's say you live in a hilly condition.
Right.
And
Right.
And the way home is kind of hilly region.
Exactly.
It's a incline.
Yes.
So in that case, whether you'll be able to
really.
Yes.
Right.
And what is the range at that condition? What can you expect?
Absolutely.
So all these things can be done.
Yes.
Many things.
So that means any real road conditions we can emulate at the lab level.
Yes.
Repetitively recreate the same situations and do multiple number of test cases and gain a confidence that whether your hardware, software, calibration is all okay.
Yes.
Right.
And major thing is we can connect as many data loggers as possible.
Absolutely.
That is the main.
On the road, when you're on an uphill, you don't want to have a power analyzer sitting on top of your vehicle and then you're driving it. Right? Yeah,
exactly.
Agree.
So if we take a look at the other graphs, so this is where the motor speed and power comes in.
All right.
And with respect to different ISOCs as well.
Got it, right.
So as we discussed before, like till 30% or 20%, it is more or less having the same power output as well.
Right.
So at the lower SOCs, we can see what is the power we can expect.
Okay.
At least like for 3% and the 1%. So this is the maximum power.
Output power. Yes. So it's nearly about 1.2 kilowatt.
Yes.
Right.
So we can see at the 100% of SOC, we can expect around 5.4 kilowatt.
Wow.
So that is what even the data sheet or the specification tells us.
Right.
And if we come below to 20%, so maximum it's below 2 kilowatt.
Right.
As it is coming to 3% SOC, it's around 1.5 kilowatt.
Right.
And as it comes 1%, it's
just right about 1
close to 1 kilowatt.
Right.
So it starts with 1 kilowatt and slowly drops.
I think this is like a 48 volt system. So
yes,
51 volt system. That's mean probably you're drawing about 20 amps of current. Still at that about a 1% SOC.
Yes.
Right. That means they have like 15 cells in parallel.
That 14, I think.
14 in this model that currently we have. That means about 1 and 1.3 amps of current for each cell. So
Yes.
that means it's operating about what point two C, 0.2 C even at a 1% SOC.
Yes.
Right. Interesting. But that's how we can dig deeper. I mean, once we get the data of the results in place.
Yes.
I think this is our mechanical output power, right? So
Yes,
there will be
yes.
conversions, efficiency losses at a motor,
Huh.
motor controller, and then also some conversion losses at the battery and components like that.
Yes.
Probably you're hitting about 0.225 C or something like that with if you accumulate all of these things in place.
Yes.
Wow, right. Good.
So,
right.
and all this power and torque, like, it is measured by our dynamometer.
Dynamometer, right. So we have inline torque sensing, so with that we capture it. So this power is the mechanical power?
Yes, it is
Right.
a mechanical power.
Yes. Okay.
Measured the torque and the speed of the
Got it, right.
So this is also done with different gradients as well.
Gradient, right.
So this is with a 7% gradient.
Okay.
And what is power? As you can see, like the speed is also much reduced here
Got
in this
Higher gradients in place, right?
Yes.
Nice.
And for 1% or here in this case it is 2% SOC.
Right.
We can expect we are trying to push more power out of it, but the speed is very limited in this case.
Got it.
So that is what happening in this condition.
Okay.
So we also have concluded some
the power
observation. That was for different gradients. So that was for different SOCs.
SOCs in place, right?
And here we have in the x-axis we have the SOC.
Got it.
Right. The y-axis we have the power.
Right.
And we can see what was the power that was observed for different gradients.
Yes.
And with respect to the SOC as well.
Absolutely.
So when we come to the lower region of the SOC, we can see the decrease in the power.
Okay.
So from till 30%, it is maintaining a constant power.
Right.
So because of the mode switching, there is a drop in SOC.
Right.
So and if we take a look at the motor torque, so with respect to different grades, so we are expecting a little bit of we are demanding more torque
from the vehicle,
and it is delivering as such.
Right. That's a significant source that our dyno is applying the load.
Yes.
As we applying the gradient, so it is applying the load, and that's why vehicle is trying to overcome that grade and then trying to produce more torque at the wheel.
Exactly.
Yes.
And this is with respect to the vehicle velocity. What is the max vehicle velocity? That was went with respect to different gradients.
Right.
So even with the 14%,
it's doing all the best.
It's doing its best.
Right.
So when it comes to the lower SOC, so we can see at 0 grade, so it is doing
it about 45.
Yes, 45.
That's a common
46.
number of eco mode, I think. Right?
Yes.
At eco mode, it performs 45.
Yes. For gradient 7 and 14, you can see there is a significant drop in the vehicle speed as well.
Right.
So that is one more observation that we have. So this is the same thing correlating to the motor speed as well.
Right. The motor maximum
yes.
operating speeds and that. Very nice.
So this is the maximum wheel torque with respect to the wheel side.
Yeah.
So if we conclude this with the energy consumption,
right.
So that was the beginning.
Wow.
Right. So this is with respect to the energy consumption.
Okay.
So how it is consuming with respect to the different SOC.
Okay.
So the consumption will be in terms of watt hour, right? And the same thing goes here as well, right? With 30% to 100% SOC, we can see there is a significant energy consumption, right? And with the lower SOC, it is much lesser, and this is for the 1%.
All right.
So the energy consumption will be very less.
Very less compared.
But still, the vehicle is for a user perspective, it is performing well. Okay. But this type of consumption or the data that you want.
Okay.
So if you put it in the dyno, and this will able to give you
the very insightful.
Yes.
I think one point when we had that gradient thing, right?
Yes.
So I think we don't know if we spoke on the last podcast or not. Is that how does a dyno replicates
a gradient?
Gradient, because you're not making the vehicle to go like this on the lab, but the vehicle is just sitting on top of the roller, but we're just telling them hey, there is 0% gradient, 7% gradient, and you're the guy who developed the whole control software. I think can you just give me some insights, like just the fun part of it, like how is it able to do that?
So to before we go there, I want to specifically mention that people often compare the dyno with something like a treadmill.
Right. Yeah.
So it's something like we run staying there still, but we are running.
True.
But however, if we can't compare the same thing with the dyno,
Right.
because the vehicle is driving there.
Correct.
Something like you are driving the roller, something like that, and the roller is not driving you.
Exactly.
In this case, in the treadmill case, the roller is just rotating, and you're just walking on top of it.
Exactly. If I assume that we can compare this to a cycler, I think there is some other type, like you sit on it and you can increase the load and that tightens the mechanism.
So the same thing if you compare it with the cycle, right? Which will be a standstill where the user just sits on top of it, and there'll be some electronic load or even the manual friction load.
Yes.
Where if you just tighten the screw, you'll feel more
effort to
be put. So the same thing we are doing with the roller here.
Got it.
And that too with a precise electronic control.
Okay.
With the close-up software, and if I command that 5 Newton meter has to be applied,
it will take a feedback and
yes, it will take a feedback and it will apply.
Right.
Fine. In less than 0.1 of a second.
Wow.
100 milliseconds.
Okay. That's a response time that we have on a dyno.
Yes. Exactly. Right. So what happens here is that when the vehicle is loaded on top of the dyno, so the contact between the rear wheel, that is the driving wheel, and the dyno will be the roller.
Got it.
So none of the other, apart from mechanically fixing together, none of them will be a rotating component. Only thing is the wheel and the roller.
Yeah.
Right. So there won't be any actual pressure on that.
Right.
So that won't affect here.
Right.
So only thing that can affect is that there is contact patch.
Right.
So we have some formulation on that to mimic that load. What is the contact patch that you need?
Right.
So apart from that, so only thing is that you have a rotational load.
Got it.
Right. So if you want to mimic anything which is uphill condition, so just apply more load. So imagine you're riding a cycle. There is an up coming.
Correct.
Suddenly you feel more pressure.
Yes. The same way what vehicle would feel.
Yes.
Right.
Same way if you do it with a cycle, which is something like an exercise cycle, which you usually see in the gyms.
Yes.
If you tighten the load, you feel more load.
Right.
With a circular mode. Right. The same thing we are doing with the electronic load.
If I just put this across, maybe from the user, viewer's perspective, is that this is not a mechanical unit that we are giving as a load. No, it's not like a mechanical brake or anything.
No.
This is our 4-quadrant load, which is acting kind of as a generator.
Yes.
We are measuring the command of a torque sensor and say, hey, I want now, let's say 5 Newton meter. So my control software now tells this regenerative load to become more aggressive in drawing more out of whatever it is possible right now.
Exactly.
And then it does it through the control system on ups and downs and PIDs. And then, okay, I say 5, until I measure 5, I adjust my, the output, input to the, the regenerative load that we have. So I think that brings up another topic, like to give an insight about, hey, what is the difference between a rope brake dyno? What is the difference between a powder brake dyno? What is the difference between an eddy current dyno? And then what do we have is like a 4-quadrant dyno, right? I think that is a super pinnacle of dynos in place.
Yes.
What do we offer to our customers today? There are maybe other limitations with definitely, because we cannot do all of these things if we have to apply maybe all type of load conditions onto the roller, if it is an eddy current or any other types in place.
Yes.
Cool. I think we can bring that into another topic of in a podcast about what is limitations of the dynos, and then what does a 4-quadrant dyno beats everybody out in place in testing things in an idea. Cool. So I think that's pretty much we are able to deep dive. Interesting. So as a summary, the vehicle's performance is in relationship with the state of charge of the battery.
Of course.
The state of charge of the battery in the back end has a relationship with the voltage, because the battery is not a constant voltage source. And henceforth, we need to play very safe in understanding the behavior of a battery and make sure that you get your best out of whatever it is feasible in the battery. And also from user perspective, user doesn't care anything about what is your cell voltages and constant source or anything. But what you want to have a decent driving vehicle without any hiccups and stuff like that on the road. And whatever you promise to customer, you should be able to deliver that, is what the customer is expecting. So our dynos can help you to validate all of these settings and calibrations and software stuff and everything. And you drive, and then the dyno repeat it and make sure you get the optimal results to make sure customer gets the best experience, right?
Exactly.
So cool. I think that's the good, interesting topic we were able to speak in today's podcast, and we'll bring up more interesting topic as we go ahead in the upcoming webinar, upcoming podcasts that we will do. Thanks, Rahul, for today's introductions. Thank you very much.
Thank you.
Thank you.